Hello AP Statistics students. In this video, we're going to take a look and start working on problems that require convincing evidence. Now I know we all hate these problems. They've been sort of the bane of our existence lately. But if they've been confusing so far, that's okay. Now we're going to start to learn an actual procedure to do them. And I hope that will make them more accessible for you. All right, these procedures to do these convincing evidence problems are called significance tests or hypothesis tests. You'll see why in a bit. So a significance test is a procedure for using observed data, all right, that's a sample, to decide between two competing claims. So let's take a look at a nice easy example of how this works. Suppose Mr. Bolt claims to be an amazing basketball player. Who would doubt that? Mr. Bolt claims to make 80% of the free throws he attempts. Who would doubt that? Now, suppose Mr. Bolt shoots 50 free throws and makes 32 of them. All right, that's our sample, right? So what is our sample statistic here? So my p hat is 32 out of 50. So what is my shooting percentage here? 32 out of 50. Whoa, only 64%. Bolt, you claimed 80%. So what does this tell us? So we now have some evidence that Mr. Bolt is lying about his 80% free throw average, right? But is it convincing evidence? That's the big question. Yes, we do have some evidence that I'm lying about my 80% free throw proportion. But is this convincing evidence? So we're going to get a procedure to sort of decide, is this convincing evidence or not? So there are essentially two possibilities here, okay? And these are called hypotheses, which is why it's called a hypothesis test that we're getting to, okay? So the two hypotheses. First, Bolt is innocent until proven guilty, okay? It's possible Mr. Bolt is not lying, and he just had a bad day. All right, was just bad luck. All right, the low proportion was due to sample variability. All right, everybody has a bad day. It was just bad luck. And in fact, his p-value, the probability, his population proportion, is actually 80%. Okay, that is a possibility. So that is an important hypothesis. So we call that the null hypothesis. All right, you probably want to write that down for sure. That is the null hypothesis. That is the innocent until proven guilty hypothesis. All right, so the way we write this, we say H sub 0. All right, H naught sometimes, I think you could call it the null hypothesis. H sub 0, is that my probability is equal to 80%. I know we have some evidence against it, but that was just bad luck due to sample variability. All right, the other possibility is that I am guilty. All right, Mr. Bolt is lying to us, All right. His actual probability or proportion of shots is less than 80%. All right. So his P is less than 0.80, which means his poor performance isn't bad luck. He's just bad. Okay, those are the two options. Now, that one is called the alternate hypothesis. And the way we denote that is H sub A. So the other possibility is that his proportion is less than 80%. Okay? And the sample we got is not anything crazy or bad luck. It's close to the actual average, or the actual proportion, which is less than 80. Those are the two options here. And we have to find evidence to see which one is actually the case. Okay? Do we pronounce Bolt guilty? Or do we pronounce him not guilty? And we'll get more into the specifics of that. Right now, I mainly want us to be able to identify a null hypothesis and an alternate hypothesis. So how would we decide between the two? Okay, well, that's where everything we've learned comes into play. A simulation or a sampling distribution. What are the chances for an 80% free throw shooter? All right, we're going to assume Bolt is telling the truth. What are the chances of an 80% free throw shooter to make 64% or less shots by chance alone? They're just having a bad day. We happen to get a bad sample from him in a random sample of 50 attempts. So we've done this before, certainly. This applet, hoping, looks familiar to you. This is essentially just a binomial distribution where the probability of success is 80%. We are doing sample sizes of size 50. Let's look at a whole bunch. I don't know, let's do 500 or something. How about that? What would 500 possible samples look like? All right, there we go. I want this to be the proportion. All right, so my proportion was 64%, right? How many of these samples are 64% or less? It looks like right here, doesn't it? That we could call that 60. That might be 65. I don't know. Let's call it 64 just to be safe. 1, 2, 3. Looks like it happened 4 times. 4 times out of 500. Okay? 4 times out of 500. That's called the p-value. So the p-value here is equal to, from our simulation, 4 out of 500. So what is 4 out of 500? 0.008. Now, technically, we could also do that with a normal CDF, right? That's a sampling distribution for sample sizes of 500 and a probability of 80%. And so we can do that on our calculator as well with simply a normal CDF. So second distribution, normal CDF. So we want 64% or less, right? So the lower is a really big negative number. The upper is 0.64. The mean is 80%. Now the standard deviation, because this is a sampling distribution, we have to change the standard deviation, right? We have that formula. It is the square root of p times q, so 0.8 times 0.20, divided by the sample size. Just plug that right in there, hit enter, hit enter, hit enter, and we get 0.002. So our normal CDF is a little bit different than our simulation, but they are both pretty darn small. All right, they're pretty close, but they're both pretty darn small, aren't they? Let's stick with our simulation value, but there isn't much difference between, not much significant difference. So what does that p-value actually mean? All right. This is something I would like you to be able to interpret. All right, assuming Mr. Bolt's free throw percentage is actually 80%. There is a probability, all right, that's why it's a p-value, a probability of 0.008 of getting a sample proportion of 0.64. That was our observed value. There's a 0.008 probability of getting a sample proportion of 0.64 or less in a random sample of 50 attempts. All right, so if I'm telling the truth, there's a probability of 0.008 of getting a sample like this one. That's pretty low, isn't it? This is giving us more and more evidence, I think, to reject Mr. Bolt's claim that he actually has a probability or a free throw percentage of 80%. All right, but we're not going to quite get all the way to deciding which hypothesis is correct here, okay? This is pretty much as far as I want to go today. Can you identify the null hypothesis and the alternate hypothesis, and then interpret a p-value? Okay, so let's take a look at two quick examples of that, and then I'll let you go. So at the Hawaii Pineapple Company, HPC, I know it well, managers are interested in the size of the pineapples grown in the company's fields. Last year, the mean weight of the pineapples harvested from one large field was 31 ounces. A different irrigation system was installed. Managers wonder if this change will affect the mean weight of pineapples grown in the field this year. All right, state appropriate hypotheses for performing a significance test. Be sure to define the parameter of interest. All right, so we need our null hypothesis, H0, and then our alternate, H sub A. So our null hypothesis is that nothing changes, all right, that the average is still 31 ounces. So the mean is equal to 31 ounces. Our alternate hypothesis, the one that we might look for evidence for, is that that mean is now different, that it is not 31 ounces, that it has changed somehow. All right, so our null hypothesis, all right, this one is kind of the beginning, innocent until proven guilty. Our beginning assumption is that we have 31 ounces for our average. And our alternate is one that we're going to look for evidence for, all right, that the mean is actually not 31, that it's changed. Now, this one could be bigger or smaller, right? Just that it's different than 31. We don't think it's bigger. We don't think it's smaller. We just are wondering, is it different? All right, they did ask us to define the parameter of interest. So that is the mean. What is this mean? What does it mean? So where mu is equal to the true average weight of pineapples harvested from this large field. All right, context, 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 right? There we're telling us what the mean is, what mu is. So, identifying the null and the alternate hypothesis. All right, and the second thing I'd like us to be able to do is interpret a p-value. That's what this one is going to be. So, calcium is a vital nutrient for healthy bones and teeth. The National Institute of Health, NIH, recommends a calcium intake of 1,300 milligrams per day for teenagers. The NIH is concerned that teenagers aren't getting enough calcium on average. Is this true? Researchers decided to perform a test of, all right, so they gave us the null and the alternate hypotheses here. So again, the null is what you believe to be true at the beginning, and the alternate is what you're testing for, what could be true. All right, where mu is the true mean daily calcium intake for a population of teenagers. As you can see, they just did the same procedure that we did in the previous problem, right? Necessary. All right, they ask a random sample of 20 teens to record their food and drink consumption for 1 day. The researchers then compute the calcium intake for each student. Data analysis reveals that the average is 1198. The standard deviation is 411. Researchers perform a significant test, oh, how nice for them, and obtain a p-value of 0.14. Ah, they did it for us. So nice. Explain what it would mean for the null hypothesis to be true. Okay. What would it mean if the null hypothesis were true? So if the null hypothesis is true, all right, now the null, remember that's H0. That means the mean is actually 1,300. The average calcium intake of teenagers, whoa, I cannot type intake, of teenagers is 1,300 milligrams? Was it Yeah, milligrams. All right, if the null is true, then the mean is actually 1,300. All right, B. Interpret the p-value. So the p-value is 0.14. So assuming the average intake for teenagers, the average calcium intake, is actually 1,300 milligrams, all right? Because that's our assumption, that's our null. Assuming that is true, there is a probability of 0.1404 of getting a sample of 20 teens with an average calcium intake of 1198 milligrams or less. All right, there's a 14% chance, a probability of 0.14 of getting a sample of teens 1198 milligrams or less, because we are checking or less than 1,300. Okay, that's kind of where that comes from. That's the sentence I'd like you to be able to write there. Can you interpret a p-value? It's the probability of getting a sample like the one you got. And can you identify the null and the alternate hypothesis? All right, that's a good start for Chapter 9. We will pick up there when I see you next.